Hello, this lecture will cover pages 109 through 116 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on combinational logic circuits, Part D, Designing Combinational Logic Circuits with K-map Techniques. Starting out on page 109, I have the first design problem. You may want to get out page number 100 in your lecture notes and have it handy. Page 100 is your combinational logic design procedure. Using the design procedure, design and realize the following circuits. Here's your specification. The customer wants you to design a circuit for them. Design a 4-bit prime number detector circuit. The 4-bit input will allow numbers 0 through 15 to be input. The output should be high only when the prime numbers 1, 2, 3, 5, 7, 11, and 13 are being input through their binary form into the circuit. Always do a block diagram. So I want you to go ahead and try to stop the video and work this problem out. See if you could do it. I'm going to go through it with you, and I like to go through these problems with you, but you have to try it on your own because it's going to look easy when I do it. You have to try it until you see the technique, and once you do it, the curtain opens and you see the orchestra and you're good to go. Here's your block diagram. Here's your prime number detector. Notice it has 4 inputs and it has 1 output. Since it has 4 inputs, therefore, you're going to have 16 states in the truth table. And you're going to use a 4-variable K-map. 4 inputs means a 4-variable K-map. The number of outputs tell you how many maps you'll need. So you only need, there's 1 output, so you're only going to have to do 1 K-map. You're going to do 1 K-map, and it's going to be a 4-variable map. So if you work the problem correctly, you'll see page 110, it's blank, a worksheet for you. But basically what I did was, here's your inputs, A3 being the most significant bit through A0, and you write these down and you count as you go. You literally count 0, 1, 2, 3, and you make sure you have a 3, and I separate groups of 4 like I said, and there's your binary 5 and 6 and 7 and 8. You do this sequentially, you won't miss any possibility. And then your prime number outputs, you write a 1 where all your fundamental products are going to be. Here's the 1 at 1, here's 2, here's 3, here's 5, here's 7, here's your 11, here's your 13. So y equals the sum of midterms, and here's the midterms. 4 inputs mean you use a 4-variable map. You go to your 4-variable map, you put 1s in where the fundamental products are. And I went ahead and I grouped these into, I got a group of 2, I got another group of 2, let's see what I got here. I got a group of 4. My largest group I could get was a group of 4, and that's this group right here. And you do this in order. You look at A3, then you look at A2, then you look at A1, and you look at A0. And when you do that, you'll see that this group of 4 is A3 bar A0. And you do it for these other groups of 2, and you'll get these other 3 expressions. Notice the smaller the groups, you have to add an addition, the larger the number of variables are represented here. If I had a group of 8 is only going to show 1 variable. A group of 4 is going to show 2 variables. A group of 2 is going to show 3 variables. Then you realize the circuit from the expression. On page 111, K-map design problem number 2. Customer hires you to design and realize a circuit with 4 inputs, A3, A2, A1, and E0, that will produce an output called valid only when the binary inputs are greater than 4 but less than 12. Assume that A3 is the most significant bit. Forget about what you're going to do with this. The customer is going to do something with this high true signature. When this input meets the desired spec, this output's going to go to a 1, and it's going to do something. It's going to drive a transistor circuit, it's going to drive a relay, and it's going to drive a motor. Don't worry about that right now. Your objective is just to design the logic that'll drive whatever's out here. Do your block diagrams. Remember, I give you credit for that. Show your inputs, show the number of inputs, show the number of outputs, and here I said 4 has to be less than A, which has to be less than 12. 1 output, therefore you need 1 K-map. 4 inputs, so you use a 4 variable map. Valid is equal to the sum of the midterms 5, 6, 7, 8, 9, 10, and 11. You get that from your truth table. This is the answer, and then you realize the circuit. Make sure on the next page you work this design problem out. See if you can get what I got. We're not going to show the realized circuit because we've done that a number of times, but you should be able to take this expression and draw the circuit for that. On page number 113, there's design problem number 3. We've seen this before in a previous lecture, but we simplified all this using Boolean algebra. I want you to do this same problem, but I want you to use a K-map reduction, and you'll see you get the same answer. You have to look back in the lecture notes and see what page this was on. You'll get the same answer, and I think you'll agree that K-maps is the way to go. Do that on page 114. Make sure you know how to do it. K-map design problem number 4, which is on page number 115. A binary 2-bit multiplier circuit. Here's the specification. Design a digital circuit that takes two 2-bit numbers, x1 and x0, and y1 and y0, and produces an output binary number, 4 bits, z3 through z0, that is equal to the arithmetic product of this times this. These are binary numbers. So let's take an example. 2 times 2 is going to give you a 4. So you only need 3 bits to show 4, 1, 0, 0. But what if this was a 3 and this was a 3? A 1, 1, and a 1, 1. A 3 times a 3, the output's going to have to be 9. If this is a 1, and this is a 1, and this is a 1, and this is a 1, that's a 3 times a 3, so you should get a 9 out here. 1, 0, 0, 1. That's why I'm showing 4 output bits. There's 4 inputs, so you use a 4 variable K-maps, and there's 4 outputs. You will need 4 K-maps, 1 for each output. You just do this 4 times, that's all. 4 outputs means 4 K-maps. So I want you to work this problem out using the design procedure that I discussed, and see what you get for an answer. You're going to have 3 Boolean expressions. You're going to have 3 circuits. Okay, the circuits all go inside here to form a 2-bit multiplier circuit. And if you do that, I know I keep mentioning this, but you really have to do it on your own. So you hit that wall. So you hit that wall and you're lost. And you break through and you learn at that point. But here's the answer. Notice I'm showing my 4 inputs. Here's my, even though these are separate inputs, list them all as together so you get every state. I don't care what order you put these in, but the point of it is when you lay out your map, look, when you lay your map out, this has to be, x1 has to be the most significant bit. Remember these K-maps that look like this? I'll do a 4 variable map here and show you what I mean. Remember I said this was A, and these last 2 rows were A, the 2 middle ones were B, the 2 last columns were C, and the 2 middle were D. And we numbered all this. We numbered these. You know, you can take a look at how we numbered. I don't want to take the time to do that. But if you look at the top of our truth table here, this here would have been your A, B, C, D. I don't care how you number this, but I don't care how you lay this out up here. Just lay it out the way, you know, the Y1, Y0, X1, X0 could be in that order. Then do your sequence 0 through 16 and count as you go so you don't miss any. And just remember, when you lay out your K-map now, the only thing you have to do is, this is an A, it's x1. This is x0. This is y1, and this is y0. This is your A is your x1, B is your x0, C is your y1, and D is your y0. You have to put those in so when you form your expression, you're okay with it. And then all you do basically is, once you have your truth table finished, you can form your midterm form here. Z3 is midterm 15. The other output, Z2, if you look down through here, is 10, 11, and 14. Z1, 1, 2, 3, 4, 5, 6 midterms. 1, 2, 3, 4, 5, 6. It's 6, 7, 9, 11, 13, and 14. And then Z0. It's like 4 separate problems. And there's your Z0. You use K-maps, and you reduce all of these, and then you form your logic circuit. And that's what goes inside that guy right there to produce that output. Probably 30 minutes worth of work. Your customer's not going to know how to do it. They're accountants, they're lawyers, they're attorneys, they're people that run companies. They just want you to do this. You put it together in 30 minutes and you charge them $5,000. That's how you make money. And that concludes this lecture.